Okay, continuing where we had left off, section 10.3 is dealing with equilibrium constants, all right? So here in this slide, you can see you have two reactants, A and B, reacting and forming products C and D, all right? These lowercase a, b, c, and d indicate coefficients, all right? So how is the equilibrium constant defined? This was derived by two scientists called Goldberg and Wage, and you can look them up online. And there's a bit of complicated math like calculus involved um, that led to this derivation. However, for the purposes of this class, this is how we can define it. Um, it's the concentration of the products, all right? So you multiply the concentrations of the products raised to their individual coefficients and divided by the concentrations of the product of the reactants raised to their coefficients. So product of the products raised to their coefficients divided by the product of the reactant concentrations raised to their coefficients, all right? And concentrations are in molarity, moles per liter. However, again, in this class, to keep things simple, we are not going to use any units here, and there will be no unit used for the equilibrium constant. This lowercase c, again, it's not a coefficient, it indicates its equilibrium in terms of concentration, all right? So the C is an abbreviation for concentration. Right, so it says write the equilibrium expression for the following reaction. So remember, it's products raised to the coefficient divided by the reactants raised to their coefficient. So first make sure that the reaction is balanced, and then remember this method of products going up on the numerator and reactants on the denominator, all right? And then just write the basic method of writing the expression, and then you can bring in the coefficients, all right? Okay, so there's a 2 going on to carbon dioxide, another 2 going on to carbon monoxide. So you finish it up with writing the coefficients. Okay, heterogeneous equilibria and Kc. So heterogeneous equilibria is where everything is not in the same phase, all right? So you have H2O, which is steam in the gas phase. You have carbon in the solid phase reacting to form hydrogen also in the gas phase, and carbon monoxide in the gas phase. In the equilibrium expression, no solids or liquids are included because solids and liquids are not subject to changes in concentrations. However, gases are, all right? You can change gas concentration by increasing, decreasing pressure, etc. But you can't apply pressure to solids or liquids and change their concentrations, all right? So in the expression, you've only included hydrogen and carbon monoxide in the products and just the water in the reactant because of the fact that carbon is a solid, it's not included in the expression, all right? Now here you have calcium carbonate breaking down into calcium oxide, also a solid. That's hard to see, that's an S. It's a little bit not legible, but this is an S, a solid, and so is this, all right? Carbon dioxide is the gas. So the Kc expression just has carbon dioxide, all right? Because that's the only gas present. So that's how you write equilibrium expressions for heterogeneous equilibria. This is another example of a heterogeneous equilibrium where you have phosphorus solid reacting with chlorine gas, forming PCl3, which is in the liquid state. So the K expression, numerator is 1 because there is nothing. You cannot put anything in the numerator. The denominator is the Cl2 raised to 6, all right? So you can have expressions for K like so, okay? Depending on what type of equilibria you're looking at. how do we calculate the value of K? All right. Once you have the equilibrium expression, if you have the numbers, numerical values of the concentrations of reactants and products, you can just plug it in into the equilibrium expression and then get the value for K like it's done here, okay? HI was 1.04, so HI square, so it's 1.04 square. Hydrogen and iodine were zero point 0.1 and 0.2 respectively, all right? So take the product of this and divide it into the square of that, and Kc value comes out to be 54. Now you can conduct more experiments where these quantities, these amounts can differ. However, if the temperature is kept exactly the same, then this Kc value, it's a constant, it will not change, okay? That's what you see here. You have different values for the concentrations of hydrogen, iodine, and HI, all right? Different numbers. However, because the temperature is maintained at 427 degrees centigrade, the Kc values are all exactly the same, 54, all right? So you can have different kind of equilibrium conditions. However, at a given temperature, the Kc is a constant, okay? If you change that temperature, then of course the Kc value will change. So Kc is temperature dependent. Also, the other thing is that we're not deliberately not putting any units in in the expression or the value of Kc. All right, so we're just using numeric values. All right, so it says here N2O4 breaks down, dinitrogen tetroxide breaks down to form nitrogen dioxide, 2 moles or 2 molecules of it. And it says, what is the numeric value of Kc at 100 degrees centigrade, if that's the reaction temperature, all right? And they've given you the concentrations of N2O4 and NO2. So just plug it in into the equation, all right? So Kc is going to be NO2 squared divided by N2O4. So 0.31 squared divided by 0.45, okay? And Kc comes out to be 0.21. Okay. Given the following chemical equation, what is the numeric value of Kc at 443 degrees centigrade? Again, it's just plug and chug. So you put in your 0.35 squared, and then this is 1.2 and 1.2, so 1.2 squared. So 0.35 squared divided by 1.2 squared. And that comes out to be 8.5 times 10 power negative 2. All right, we will stop here, continue this in the next video. Oops, sorry.